In this video, we're going to talk about something called nullity. And nullity is just the dimension of the null space, but we need to figure out how to find it. There are a couple of different ways we can do that. I want to start with a matrix A. This is the one we've been working with for the last couple of videos. And we found that when we row reduced this matrix to echelon form, we got this matrix. And I haven't been using this notation, but your textbook does this. It says because this is row equivalent, this matrix here is row equivalent to the original matrix, and it's an echelon form, it's calling this A prime. Now, by way of a reminder, you can find the rank of A by finding the pivot columns of A prime and simply counting them. The rank of A is the number of pivot columns. In this case, it's 3. If we take the pivot columns that we found in A prime, or that we found by putting it in the form of A prime, and we go back to the original matrix and we find the corresponding columns, those 3 columns are linearly independent and they form a basis for the space that we're in. Here we're in a 3x4 matrix. We have 3 entries in each column, so these 3 linearly independent columns, which can be represented by vectors, are a basis for R3. The other thing I want to remind us of is that the other way to think about the rank is as the dimension of the column space. If I take the column space of A and find its dimension, what we say about this dimension is that it's based on the number of linearly independent columns, right? The number of pivot columns, which tells us the number of linearly independent columns. We call that the dimension of the column space of A. And the fancy name we give to that is the rank of A, but it's a dimension, and that's going to be important in a minute here. Now that I found the linearly independent columns, let's take a look at what the other columns, I've got the wrong tool again, I want the highlighter. What do the other columns tell us? Well, this column is linearly dependent on the other columns. It can be written as a linear combination of these other 3 columns. And I don't know if you've cottoned on to this yet, but a column is either linearly independent, cannot be written as a combination of other columns, or it's linearly dependent. It can be written as a linear combination of other columns. It can't be both, and it can't be something in between. So that means that the number of linearly independent columns and the number of linearly dependent columns in a matrix have to add up to the number of columns in the matrix. The other way to think about it is to say that there are 3 pivot columns and 1 non-pivot column. And together, those add up to the total number of columns in the matrix, 4 columns, 3 that are pivot columns and 1 that is a non-pivot column. Well, we call the number of pivot columns the number of linearly independent columns. Oops, I got my M and my N backwards there. Columns. We call that the rank of A. And if I add to that the number of non-pivot columns, or I could think of it as the number of linearly dependent columns, I would get the total number of columns. In A, in the matrix A. And I don't need to write this out again, but I guess I will. And so I have 2 different ways to think about this. The number of pivot columns plus the number of non-pivot columns add up to the total number of columns in the matrix, or the number of linearly independent columns and the number of linearly dependent columns add up to the total number of columns in A. Well, either of these is what we call the rank of A. And so if I want to find a way to add up the rank of A with something else so that they add up to the total number of columns in the matrix, then I need a name for this thing. And what we call that is the nullity of A. Remember at the very beginning of this video, I mentioned that, reminded you that the rank of A is just the dimension of the column space of A. So let me write that one down as well. The rank of A can be thought of as the dimension of the column space of A. And so now I need a way to think of this as a dimension. The dimension of what? Well, it turns out that the nullity is just the dimension of the null space of A. So in our example up here, matrix A has 4 columns. The number of pivot columns, as found by putting the matrix into echelon form and counting the pivot columns, the number of pivot columns is 3, 1, 2, 3. The number of non-pivot columns is 1. And these two add up to 4, which is the total number of columns in A. Finding the pivot columns helps us find the number of linearly independent columns in A. If we know the number of linearly independent columns, then however many columns there are total, the rest must be linearly dependent, right? So if we know the number of linearly independent and dependent columns, they must add up to the total. If we know how many independent columns there are out of however many total, then the rest must be linearly dependent. The dimension of the column space and the dimension of the null space together add up to the total number of columns in A. These are all just different ways of saying the same thing. The main point in the previous video was to define what it means to be a nullity, the nullity of a matrix, and that is that it's just the dimension of the null space. But what does that tell us? It tells us, together with the dimension of the column space, it tells us the total number of columns. Or if you know the total number of columns, which is actually more common, right? You'll see a matrix and you can count its columns quite easily. Once you've determined what its rank is, you'll be able to determine what its nullity is, because the nullity, not something you have to compute necessarily, it's a dimension. And so if you know the rank, you can simply compute this other dimension, right? You know the dimension of the column space, you can compute very easily the dimension of the null space, which is called the nullity. In the case of an M by N matrix, which is what we've been using M by N for all of our matrices, that number of columns is N. So we can say that, why is that not going away? There we go. We can say that the rank plus the nullity equals N. In the case of our example, since the rank is 3, the dimension of the column space is 3, that means that the dimension of the null space, which is what we call the nullity of A, must be 1, because we can see that there are 4 columns. And if we know that this is a 3, that must be a 1, so that they add up to 4. That's it. N equals 4 here. A is a 3 by 4 matrix. So N is 4. These 3 tell us about the rank of the matrix, the dimension of the column space. There are 3 linearly independent, or 3 pivot columns. Therefore, the nullity is 1. Let's take a look at one more idea here, and that is, how big can the nullity of a matrix be? We'll start by establishing the matrix we're going to work with, and I'm just going to randomly choose a 5 by 11 matrix. What is the smallest possible value? The smallest possible value for the rank of B. Going back to the idea of rank, we have a 5 by 7 matrix, so we have 1, 2, 3, 4, 5 rows, and 1, 2, 3, 4, 5, 6, 7 columns. Each of these dots just represents an entry in the matrix. Okay, it's not necessary. I have a really hard time understanding new ideas if I can't see them. This is not true for everybody, but if I had a matrix that was made up of 5 rows and 7 or 11, 7. I said 11, didn't I? That was 7, 8, 9, 10, 11. Okay, what is the smallest possible value for the rank of B? What that is asking me is, what is the smallest possible number of linearly independent vectors? Is it possible for there only to be 1? Well, for a vector to be linearly dependent, I'll use a highlighter, but I'll use a different color for that. Let's say this vector is, this column is linearly dependent. Then what that means is that it can be written as a linear combination of the other linearly independent vectors, or the other columns in the matrix. Is it possible for every other vector, every other column in this matrix to be able to be written as a linear combination of this one? And the answer is yes, because I could write, let's call this one A1, it's a vector. This one could be 2A1, and this one could be 5A1, and this one here could be negative 3A1, and so on. Each one of these might be, in some unknown 5 by 11 matrix, each one of these could be a multiple of A1. And so it is possible to have only one linearly independent vector in a matrix of any size. And so the answer to this question is 1. Okay, so now let's look at what the second question here is asking us, is what is the largest possible number for the value of the rank of B? Is it possible for, where's my pen? There it goes. For there to be, well, how many linearly independent columns can I have? Could I have, say, 6? Got that here. 1, 2, 3, 4, 5, 6. Can all 6 of those be linearly independent? I'm going to pause just for a second. I'll stay on screen. I want you to think about that. How would you find the linearly independent columns in a matrix? What if you reduced it to echelon form? Would that help? What would that tell you? It would give you the number of pivots. Can you have 6 pivots in a 5 by 11 matrix? Could you have 6 pivots in a 5 by 5 matrix? Or a 5 by 12 matrix? What about a 5 by 6 matrix? Could you have 6 pivots there? The answer is no. You can only have as many pivots as you have columns, right? If you put this into reduced echelon form, you're going to get pivots. At the very most, you're going to get pivots in those positions. So the answer to the second question is 5, which is equal to our M. It would be interesting to ask the same question about a matrix. Let's call matrix C let's call it an 11 by 5 matrix. And that one is going to look like this. I've done a terrible job of drawing my dots in straight lines here, but there's really not a lot of space to do it. So let's assume that this matrix has also been reduced and is in echelon form. Then my pivots would be there. There are also there only 5, maximum 5, right? There might be fewer because we might end up with a 0 row, we might end up with a free variable, but the most we can have is 5. In this case, that's our n value. And so what we say here, and we've touched on this before, I don't think I did a very good job of explaining it here, but the rank of a matrix A is always going to be less than or equal to either M or N, whichever is smaller. So we say the minimum of either M or N, the minimum of the values in this collection of values. Okay, so if you have a 12 by 17 matrix, then the rank could only be 12. If you have a 19 by 4 matrix, then the rank could only be 4. It might be less. It could be as low as 1, but it's definitely not going to be bigger than the minimum of either the M dimension or the N dimension. Okay, one last question here. What is the smallest possible value for the nullity of A? Well, if we do just a little bit of arithmetic on this equation right here, we get that the nullity of A is equal to the total number of columns minus the rank. So I'll make a note of that. Nullity of A is equal to the total number of columns, which is n, right? It's always going to be n. It's going to be 11 in this case, but I'm trying to generalize as I go here. So minus the rank of A, and actually it's the rank of B, and the nullity of B. Right? I'm working with I chose a different matrix because I chose a different name because I chose a different matrix because I didn't want it to get confused with the matrix we were working with up here. This is clearly a 3x4 matrix, not a 5x11 matrix. So they're obviously different matrices. And so I wanted to give it a different name as well. So n in this case is 11. And we've established that the rank is smaller, less than or equal to the minimum of the two values m and n, whichever is smaller, m or n. It's possible to argue that with, for example, a square matrix, an 11 by 11 matrix, this would be 11, and so we'd have 11 minus 11 is 0. So the smallest number we can have here is a 0. But in the case of the matrix we're actually given, a 5 by 11 matrix, this number is going to be 5. Since the rank is less than or equal to either 5 or 11, whichever is smallest, then that's what this value is here. It's the minimum of those two values. So that number here is going to be 5. Let me just go ahead and write that in. So it's going to be 11 minus 5. But, where's my pointer? The rank is less than or equal to, and I'm taking a large number and subtracting off a smaller number. So that means that this symbol here really should be a greater than or equal to. It's a delay on my pen for some reason. And that's going to be equal to 11 minus 5. And that is equal to 6. So the smallest possible value for the nullity of A in this case is 6. And that is the rank-nullity theorem. The meat of it is right here. The rank of a matrix plus the nullity of a matrix equals the n value, the number of columns in the matrix. That's pretty much it. We did a little bit of an example here, and we used the rank-nullity theorem down here to determine what the smallest possible value for the nullity of A is.